we are looking into actually the so-called applications of Gauss law. Right. So-called because it is not only Gauss law. One more fact that flux lines emanate from a charged surface in the direction perpendicular to the surface if it is positive charge, and get terminated on the surface in the direction perpendicular to the surface if it is negative charge. And any charge of q coulombs emits q coulombs of flux is what is basically given by Gauss law. Whatever may be the surface that you take, the total normal flux passing through the surface is equal to the charge enclosed. That is only is given by Gauss law. Now listen, this is what we were doing. Even though we did actually a few things, I will just talk about it now. In the applications of Gauss law, the first two applications are the determination of electric field intensity at any point because of infinite line charge. We did it. And the field intensity at any point because of infinite surface charge. Whether you use so-called Gauss law or derive the expressions, they are one and the same, because of which we got the confidence to use this Gauss law to determine the electric field at any point because of a given charge distribution, provided, to repeat, provided the field has certain type of symmetry. In all these cases that we look into now, it is not possible for us to determine the electric field intensity at any point, given the electric field intensity at any point because of a point charge, using integration. It is not possible. When it is not possible to do it, we will determine the field using Gauss law. One such thing that I spoke about was, now you can ask, a hollow spherical charge of q coulombs distributed, charge of q coulombs distributed on a hollow spherical surface of radius A. And we had the discussion about how the charge will be there on this surface, because of which we can say charge resides only on the outer surface of the spherical sphere. There will be no charge on the inner surface. But if it is a plane surface, there is nothing like outer surface and inner surface, because of which half of it will be there above on one surface, half of it will be there on the other surface, because of which per unit area or ρs will be the surface charge density. Check it. Some good things we will see today. In the applications of Gauss law, listen carefully. whenever we want to determine, now in all the applications, let us say the electric field intensity at a point, draw a regular surface through the point of interest in such a way that it is everywhere perpendicular to the flux lines. Because it is the regular surface always in these cases, we will know the area, expression for the area of that surface, knowing the amount of flux passing through it. We can determine the flux density at any point on that imaginary surface drawn through the point of interest. We will know it in direction as well as magnitude, divided by epsilon of the medium in which we are looking at the field expression. We will get the electric field intensity. This charge Q sends the flux out in all the directions equally. The way in which the charge distribution is visible from a distant point is same for all the points on an imaginary concentric spherical surface of any imaginary concentric spherical surface. I did not draw properly, but okay, I'm telling that it is concentric spherical surface. Because the distribution is similar. I don't know whether you are in a position to properly appreciate this statement or not. Please check it. Because of which we say that the field of this spherical charge exhibits spherical symmetry. Exhibits spherical symmetry. Now, I feel that, okay, fine. You may not be in a position to tell whether you understood that or not also, because I'm talking about symmetry now. I will explain it in a different way. So that when I feel that I should be explaining this, I have to do that, because of which I'm talking. Please observe. Any given spherical charge let us say I want to determine the field at a point which is at a distance r from the center of the sphere. I can consider this spherical surface to be for sure, concentrate, the combination of so many ring charges. You agree? So many ring charges like this, so that the point of interest is on the axis of all the ring charges I can consider of different radii, because of which we know that on the axis of a circular ring charge, the field is axial. Same thing. if I consider this point, I can say that again similar ring charges are there from this side, because of which the field here will be seen. If I consider the point at the same distance along this line, what did I have to do? I have to consider this sphere to be so many circular charges like this. Everywhere I am considering the spherical charge to be the combination of so many ring charges in such a way that the point of interest is along the axis of every ring charge that I have considered on the sphere. It's a surface charge. Because the way in which I can divide the sphere into so many circular charges is same for the sake of every point. Ultimately, the axial field should be same because I'm there at the same distance from the same charge. One example may help because of which I spoke. No, axial to those circular conductors. Axial to those circular conductors. Here it is radial to the sphere. Any point that you talk about can be considered to be the radial. We will talk about the distance from the center only, because of which it is a radial distance from the center. For ring charge, is it radial or axial?
Axial, sir.
Okay. For the sphere, it is radial.
Okay, sir.
Ultimately, in the spherical coordinate system, for the sphere, these field lines are radial lines. For the one point maybe required for us to talk about it. You may always get a doubt like, no, anyway, I have defined elementally differential surface on any spherical surface. I can divide the entire surface charge as the combination of so many infinitesimally small surface charges. Then I can divide it and represent it as infinite combination of so many differential surface charges. Why we can't determine the field at any point in the field, electric field intensity at any point in the field? By using integration? Because we should be in a position to mathematically represent the vector from a general point on the spherical surface to any point in the field. We know very well that in cylindrical and spherical coordinate system, it is not possible to mathematically represent the vector from any point to any point. Only from limited cases there are. Because it is not possible to represent a general vector from any point on the spherical surface to the point of interest, we cannot determine it. Now, to determine the electric field intensity, at a point, let us say this. Due to this spherical charge distribution, I told you that you have to draw a imaginary concentric spherical surface of radius r passing through the point of interest. This is r. Definitely the flux density d bar is equal to 0, first of all, for r less than a inside the sphere. And for r greater than or equal to a, it is for sure q by 4 pi r squared, because The charge emits q coulombs of flux which passes through the sphere of radius r for all r greater than or equal to a. Okay. So the electric field intensity is equal to 0 for r less than a. Q by 4 pi epsilon r squared for r greater than or equal to a. That means are you comfortable? I'm giving the next point. Looking at the expression. Whenever I want to determine the field, at any point outside the sphere of radius a containing a charge of q coulombs, we can assume that entire charge is concentrated at the center. You please tell me, instead of q distributed on the sphere of radius a, if the same q is there at the center of the sphere, that q is also at the same distance from the point, and the electric field intensity at that point is radial because of that also. It can be assumed to be concentrated at the center of the sphere to calculate the field at any point outside, not inside, of course. Is it clear? And that is what I was talking about also yesterday. If I draw the field intensity graph as a distance function of r, till r it will be 0. There, till a it will be 0. It suddenly increases to q by 4 pi epsilon a squared, and later on it is q by 4 pi epsilon r squared. This is at any r, this is a, r equal to a. For any r, it is q by 4 pi epsilon r squared, provided that r is greater than or equal to a. This is number one. Number two, single charges only, let us look into. Suppose, not possible of course, suppose, hypothetical case totally, a stable volume charge of this shape is very difficult to get. If there is a volume charge in the form of a sphere, everywhere charge is there, and I say that the charge density is rho v. If the volume charge density of the charge inside this spherical volume of radius a is constant and is equal to rho v, one case. This is where actually we should have understood Gauss law properly. I want to determine the electric field intensity at any point outside and inside the sphere also, because charge is there everywhere. And for sure, you consider any spherical surface of radius r which is concentric to the sphere, the field distribution on that spherical surface, imaginary spherical surface of radius r, should be same everywhere. For sure, because it is sphere. In fact, if you want to understand it further, now the spherical volume charge can be divided into so many circular disk charges with varying radius, from 0 to maximum to 0. They are disk charges. spherical surface charge can be divided into rings, whereas spherical volume charge can be divided into so many circular disks of varying radii. From 0 to maximum it will go, and then again decreases. Any field is on the axis of this circular disks, because of which it will be radial wherever you go. Now let me now do this. Definitely, when I try to look at the field outside, it will be spherically symmetric, because of which whenever I want to determine the field at any point which is at a distance r from the center of the spherical charge, I will draw a sphere of radius r, concentrate to this, because of which it is everywhere perpendicular to the flux lines, and the flux density will be radial, and this b bar equal to what? First of all, for r greater than or equal to a, I am looking at. Please look at it. Rho v into total charge inside the imaginary spherical surface of radius r is what? Rho v into 4 by 3 pi r pi a cubed is the total charge on this spherical volume divided by the area of the spherical surface of radius r, because I want to know the flux density, is what? 4 pi r squared. For r greater than or equal to a. Please concentrate. Is it correct? Total Q inside this, because it is concentric sphere, it is everywhere normal by naturally, and at each and every point flux density is same, because the field intensity is, because of which field intensity is also same. That is why we spoke about the spherical symmetry of this particular field. Comfortable? For all greater than or equal to a. I want you to respond. For r less than or equal to a. For r less than or equal to a also, inside the sphere, there is certain amount of charge, because of which flux lines will pass through it. But there is charge outside also. Will it matter for us? Will the charge outside the closed surface matter to talk about the flux density at any point because of it? No. That's what we spoke during the Gauss Law itself. Because of which I need to calculate the charge inside this spherical surface of radius r when r is less than a as what? Rho v times 4 by 3 pi r cubed. Earlier it was full sphere of radius a. Now whatever is there inside only will matter for the flux and flux density, divided by 4 pi r squared. For the AR is fine everywhere, radial. For R less than or equal to A. Check it once. For somebody who is going to study fields as a subject in the semester, makes a difference actually. We may not use this. The next case, we will use it for the sake of discussion, at least. Spherical volume charge. Everywhere charge is there, not on the sphere. The only place where we really can see stable volume charge, stable volume charge is the impurity ionic concentration on either side of the junction, which is positive on N side, negative on P side. That's all. That is the only place where I really have seen people, really, it will be there also. Uncovered volume charge will be there. Normally, whenever you charge an object, the charge comes onto the surface. Another place where unstable volume charge is there and the discussion actually happens is the gun diode, where a domain of a charge is formed. A charge cluster is formed and it travels. While traveling, it grows, is what is another point for us. That is actually unstable volume charge. We don't see stable volume charge, but I told you in the beginning itself that so many things that we talk about here as charges are hypothetical in many cases. You should not really think about whether that exists or not. Don't worry about it. If it exists, I'll tell you this is practical. Parallel path capacitor I spoke about. Practical. It exists. Can be measured. Is used also. Comfortable? So electric field intensity is what? Final expression? E bar is equal to inside. What is the final expression? 4 will go rho v r by 3 epsilon.
Yes, sir.
Rho v r by 3 epsilon. You are supposed to know something here. For r less than or equal to AR radial. Means what? From center, it increases from 0 linearly. To which value? Rho v A by 3 epsilon at A. Because this formula is valid for r less than or equal to A also. It's a continuously varying field. There is no sudden change in the field. What is the other expression now? Rho v A cubed by 3 epsilon r squared for r greater than or equal to A. You have to see that this AR. For r is equal to A, both give the same expression. Should give, if you are right. Carefully look at it. A is a constant. When I look at the way in which the electric field intensity varies as a function of the distance from the center, is what? For r less than or equal to A, till A, it increases linearly. Because it is raised to the power r, right? Directly proportional to r. Later on, by r squared is non-linearly decreasing, right? What is this maximum value? Rho v A by 3 epsilon.